Development Pharmaceuticals in association with Higher Secondary Principals Forum.
Namaskar. Hello viewers and very warm welcome to this second session on current electricity. In previous session we have discussed some concepts of current electricity. That was a part 1 we have considered as, and this is second session on current electricity. Let's revise, let's recall what we have discussed in the first part on current electricity. So in the first part, we have defined what is meant by current. We have seen the concept of current. Current on account in the conductor is on account of the electrons. Electrons are the carriers of current in the conductor. These electrons are not at rest. In absence of electric field, these electrons are constantly rebounding with the metal ions. In presence of electric field, these electrons are colliding, but they are having a drift, average drift against the direction of the field. And that constitutes a current. We have discussed about drift velocity, what exactly happens inside the conductor when the electric field is applied, how to apply that electric field, just apply a potential difference between the ends of the conductor. Electric field sets up in the conductor and electrons start drifting towards the higher potential. On the way, they collide with the metal ions, though they experience number of collision, and in presence of electric field, they start drifting towards the higher potential side. Then we have discussed about what exactly is resistance, resistivity, what does Ohm's law state, resistance, resistivity, what are the factors affecting the resistor and resistivity? Various factors we have seen, and we have discussed that as a temperature, one of the important factors, as the temperature increases, the resistivity also increases because electrons suffer more collision. So what exactly happening inside the conductor is, this is suppose a metal ion. This metal ion which is there inside the conductor, this is the electron which is coming, colliding with the metal ion. The path is straight after the collision or before the collision, path is straight in absence of electric field, but path may be curved in presence of electric field. When the temperature is increased, this metal ion starts vibrating about the mean position, and this coming electron will suffer more collision. And that's the cause of increase in resistance of a conductor when the temperature is increased. Then we have seen what is meant by relaxation time is average time between the successive collision. And this average time decreases as the number of collision is increased. And that number of collision increases on account of the increase in temperature. Then we have discussed about the resistor, resistivity. Some questions also we got the answer to that. Though the electrons are drifting from low potential towards the higher potential, that doesn't amount that all the electrons have to travel all the way from low potential to higher potential to constitute a current. As soon as the electric field is set up in the conductor, electrical signal travels at the speed of light. So you don't need to have electrons to go from lower potential to higher potential. Sometimes the question will arise in your mind, electron is so small, and how it amounts to 1 ampere current and so on. So what is the reason behind it? Though electron is small, it has small charge, 1.6 into 10 raised to minus 19 coulomb, but the number of electrons are enormous. In a metal, you can say 10 raised to 29 electrons per meter cube. Can you imagine? So that is the number in that volume, and that's the reason that amounts to a current. Now these electrons are not drifting, they are average drift towards the high potential against the direction of the field. Now if you go through NCERT book, there is a lovely problem solved comparing the drift velocity of a copper by taking 1.5 M current, and the drift velocity of copper is just 1.1 millimeter per second. Whereas the drift velocity, if you compare more or less on an average 10 raised to minus 3, 10 raised to minus 4 meters per second. And if you see the atoms which are getting excited, their velocity is much higher than the drift velocity of the electrons. And the beautiful comparison is done. Just go through that particular numerical, which is solved in NCERT book. So even atom excite or even atom vibrates at better speed than the drift velocity of the electron. So this is compared, and you go through this. So we have discussed this number of collisions. You can see this particular, I hope you can recollect this particular diagram which I had given you in the previous session, also shown you in previous session, how exactly this collision takes place. This is a very important part of the first chapter. Then you have a resistor, resistances in series, and so on. Now we'll go to the next part. Next part, we are going to discuss more concept. So let's try to understand more concept based on this part. First, we'll go in discussion of electrical energy and power. Now, as I told you, electrons in the conductor, when they are moving from lower potential to higher potential, they are colliding with the metal ion. They are colliding with the metal ion. So question will arise, when they are colliding with the metal ion, are they traveling at a varying speed? Are they having a kinetic energy? They don't have final kinetic energy as such, but they have average steady drift velocity in the direction against the direction of the field. So this particular energy then transferred to an atom, and atoms, metal ions, I meant to say metal ions. And these metal ions, during the collision, the metal ions, the electrons share the energy with metal ion, and metal ion gets that thermal energy and it vibrates. So if you try to pass current through the conductor, this is what happens. And if you pass a current for a more time, metal ions will get more and more thermal energy on account of this. And this is what is exactly the heat that is dissipated in the conductor. We'll calculate that heat dissipated and will then more or less come to a simple expression for power. So initially, if I take amount of charge delta Q in a conductor of resistance R for time t, delta t, and after applying a potential difference of V, then energy dissipated as heat is given by delta W is equal to, it's a work done, so charge into potential difference. So charge is delta Q V, but charge I can write in terms of current, I into delta T. So we get beautiful relation I delta TV or VIT, if you want to remember in different way. So energy dissipated is energy gained by the charges, and that is VIT. If you want to define electric power, that is a rate of doing work. So rate of electrical energy upon time, that will be a power. VI, I can write it as V square upon R or I square bar R is a power loss, and the unit is watt. And the unit of energy, electrical energy, is kilowatt hour. Kilowatt hour is the unit of electrical energy. 1 unit which is consumed, we say 1 kilowatt hour. Another formula, we have output power upon input power as the efficiency. Multiply by 100, you will get percentage of efficiency. And heat produced, one can write in the formula I square RT. Now, the electrical energy which is transported with the help of a cable which is put on the cable, there is a lot of loss of energy that can take place. But in this electrical transmission, how the energy is curtailed, how the power loss is curtailed. Let's try to understand that also. So electricity generated at the station has to be transported over a long distance. Now, for example, Goa don't have their energy creation plant as such. Most of the electricity, we get it from the western grid. Goa needs about 1000 megawatt of power, and we get most of the power from western grid, and for south side it is from southern grid. This particular electricity comes all the way on the cable which is put, and the procedure is with the help of a step-up transformer. the voltage is step up, and then put it on the high tension, we call this as a high tension line, and then with the help of a step down transformer, it is then reduced to a safer value and then give it to a consumer. So what exactly, how we can find out this power minimization in this process? So if I take RC as a resistance of a cable, power generated at the station will be VI, I will be P upon V, V is the voltage, I is the current. Power dissipated in the form of heat, power loss is PC is equal to I square RC, where RC is the resistance of the cable. If I put I is equal to P upon V, we get this beautiful relation. And from this beautiful relation, you will come to know, if you want to reduce the power loss, PC, we have to increase V. So these voltages step up by using a step up transformer. It is put on the cable, it is called a high tension line. With the help of step down transformer, it is reduced to safer value. So this is what is done to decrease the power loss. Now, if you want to do some sort of calculations based on this, suppose a problem is asked, if you want to find out what is the electricity tariff, if so many units, so many bulbs or so many electrical elements that are used throughout a month or a day, you can easily calculate that. So how exactly it could be calculated? Simple example we can take. Suppose we have a 100-watt bulb. 100-watt bulb goes for 2 hours per day. How much is the electrical energy consumed? One can find out in 1 month. Electrical energy consumed is power into time. So power is 100-watt bulb divided by 1000, make it kilowatt, 2 hours. This is for 1 day, and if you multiply by 30, you will get 0.2 into 30, which will be 6 unit, and then total power, whatever 6 unit, that 1 unit is 1 kilowatt hour. And now if you see the rates that is charge in Goa, up to 100 units they charge 1.4. This is a chart which is released by the electricity department. And highest it says 4 rupees. So if I consider 4 rupees and multiply by this 6, so it will give you 24 rupees. So 100-watt bulbs going for 2 hours in a month will give you a bill of 24 rupees. So likewise, you can calculate what is the bill, what is the tariff, what will be the electricity bill if there are so many units running in your house, whether it is an electrical heater or a geyser, or a fan or any other. Only thing, the wattage you should know. Heater has very high wattage, fan must be having lesser. So we can easily calculate the electricity bill that one can get if you know the wattage of the units and time more or less. So this type of examples one can see, one can solve. So this is about how based on power. I'll show you more examples based on this later. Let me finish this particular part. Let's discuss now what is meant by EMF of the cell and internal resistance. Now I told you, once the electric field is applied between the ends of the conductor, electrons start drifting opposite to the flow of, opposite to that of the electric field. How to create that electric field all the time so that electrons are in continuous motion towards the higher potential? It is by way of applying potential difference. Potential difference is provided by a battery. So battery is nothing but the electrolyte having electrode inserted in it, and that chemical energy is converted into an electrical energy. How exactly that happens, that electrochemistry you study in chemistry part. But what exactly happened, what exactly we have to measure in this case, that we learn in physics. So if you want to understand the cell, so cell is basically containing of electrolyte. Electrolyte is a solution which can conduct. There are two electrodes, positive and negative. These electrodes, positive, we say that potential of that is say V plus. Potential of negative electrode is V minus, then EMF or electromotive force is nothing but potential difference between the terminal of this electrode when cell is supplying no current. So when cell supplies no current, the potential difference between the ends of this cell is called as EMF of the cell. It is electromotive force. It doesn't mean that it is a force, it is an energy. So this is electromotive force, which is V plus minus minus of V minus. Now, what is meant by internal resistance of the cell? Internal resistance, as you know, what is the cause of the resistance in the conductor? In the conductor, electrons are the carriers of current. Electron collide, that gives rise to a resistance. In the solution, ions are moving against the background of other ion. They are colliding, that gives rise to a resistance. That resistance is called as internal resistance of the cell. And that resistance we denote as small r. So, what is the cause of internal resistance? You know, it's a collision among the ions in the solution itself. Factors affecting the internal resistance. There are so many factors. Internal resistance might depend. Separation between the electrode, nature of the pair of electrode, temperature of the electrolyte, concentration of the electrolyte. These are the so many factors on which the internal resistance of the cell might depend. So, if you connect this to an external resistance R, we can write down the potential difference between P and N. So, we have connected this cell to the external resistance R. So, potential difference will be given by V plus minus V minus minus IR, where IR is the potential drop across the internal resistance of the cell. And if you put that V plus minus V minus as EMF of the cell, we get terminal potential difference E minus IR. So, when the cell is supplying current, terminal potential difference is E minus IR. When the cell don't supply any current, I is 0, terminal potential difference is EMF of the cell. So, if you just get the battery from the market and if you take a good voltmeter, ideal voltmeter to measure the voltage across it, you will get the EMF of the cell. But if you measure the potential difference as the cell is sending the current in the adjacent circuit, then it will be less than the actual EMF. If you substitute this, from arranging this, you will get I is equal to E upon R plus R, and this formula you can get. You can find out the internal resistance also rearranging this term E by V minus 1 into R. So we can use this formulas later whenever situation arises in the form of a problem. Now, we can write this formula V is equal to E minus R and rearrange it. Then E minus IR or V is equal to minus R plus E. This equation is similar to straight line equation Y is equal to mx plus C. And if you try to plot a graph of V versus I, then straight away this you will get at current is 0, terminal potential difference is the EMF of the cell. So here in this situation, in this graph, EMF is 3E, that is the battery which is used, and maximum current it can use is 3I, and the slope of this graph will be the internal resistance of this cell. And if the cell is being charged externally, then V is equal to E plus IR, and that you can understand. So this is about internal resistance, EMF of the cell. Now, let's write down the symbol for the cell and how exactly one can represent cell in the diagram. Now, suppose the symbol of the cell is this way. I hope you know the symbol of the cell. This is suppose the internal resistance of the cell. This is the way how we represent a cell in the diagram. This is the EMF, R is the internal resistance. So sometimes we draw a cell this way and write 2 volt, 2 ohm. What does it mean? 2 volt is the EMF of the cell, 2 ohm is the internal resistance of the cell. So now let's see combinations if the cells are put in combination. First we'll see cells in series. These are the 2 cells put in combination having internal resistance E1 and R1. E1 and R1 is the internal resistance of cell of EMF E1. R2 is the internal resistance of cell of EMF E2. Now, total potential difference between AC. So, total potential difference between A and C. Now, since they are connected in series, common current will flow through this, and we have potential difference between A and C is equal to potential difference between AB and potential difference between BC. You add it. Now, these I can write as, since formula we have is V is equal to E minus IR. From the previous discussion, we can write this as E1 minus IR1. This I can write as E2 minus IR2. Current is constant because they are in series. So, potential drop between AC will be equal to E1 plus E2 minus I into R1 plus R2, and this is nothing but potential difference is E equivalent minus I times R equivalent. So, if you put cells in series, you get equivalent EMF as E1 plus E2 and equivalent resistance as R1 plus R2. These are the beautiful relations you have to remember, R1 plus R2. If there are n number of n number of cells are connected in series, then equivalent EMF will be n times E. If there are n number of resistances, the internal resistance of that R equivalent will be n times R. So, that will be the formula you can go through. This is about cells in series. Now, we will see cells in parallel. In parallel, what will be the situation in that case? So, now we have cells in parallel. So, how the cells will be in parallel we can draw. So, this is one cell, this is another cell. They are connected between the two common points. Okay? This cell is having internal resistance R1, this cell is having internal resistance R2. R1, E2, R2. Suppose the current shown is away from the positive because electrons are moving towards that. So, current here is this, current gets added in this branch, it will be I. Now, let us recall that particular formula, V is equal to E minus IR. So, we will have, we can write this I as E minus V upon R. So, for each formula, now if you apply, this is drawing a current say I1, this current is drawn as I2. So, total current I is equal to I1 plus I2. Okay? So, now you substitute this using this formula, you will get E1 minus V upon R1. V is the common potential difference between the two ends, since they are in parallel, and this we can write as E2 minus V upon R2. Now, we will rearrange and solve. So, this I can write as E1 upon R1 minus V upon R1 plus E2 upon R2 minus V upon R2, and then we can resort to the final formula by rearranging E1 upon R1 plus E2 upon R2 minus V 1 upon R1 plus 1 upon R2. Okay? Now, this is what we get. Now, if you transfer this is what we get. So, if you transfer V into 1 upon R1 plus 1 upon R2, E1 upon R1 plus E2 upon R2 minus I. Okay? And this, if you try to divide this, so V will be equal to, we want to get this in this form. Okay? So, V will be equal to E1 cross multiply R2 plus E2 R1 upon R1 into R2. This is what will be left. And if you divide this, you will get R1 R2. This I can write as R1 plus R2, R1 plus R2 upon R1 R2. So, R1 R2 will go up. This will be R1 plus R2 minus R1 R2 upon R1 plus R2. So, this we can get E1 up R2 plus E2 R1 upon R1 plus R2. And this you will get minus I into R1 R2 upon R1 plus R2. So, V is equal to E equivalent minus I into R equivalent. So if they are connected in series, parallel, the equivalent EMF will be E1 R2 plus E2 R1 upon R1 plus R2, and R equivalent will be equal to R1 R2 upon R1 plus R2. This I can write as 1 upon R1, 1 upon R2. This I can write as E1 upon R1 plus E2 upon R2. And this I can write as 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. So these are the equations you can draw. I have tried to do it because it is not done in detail in the entirety book how it is, how exactly, how to resort for this particular equation. That's the reason we have gone through this. Okay, so this is about cells in series, cells in parallel, and this is called combination of cells. Now, let's see some examples based on this part. Now, if the cells are in series, I told you, if this is a cells are in series, the EMF gets added. If the cells are in parallel, then the situation is different. But if these same cells are like this, they oppose each other, in that case, the total EMF will be E1 minus E2. The small points you have to remember to solve this type of situation. So we have a situation here where the cells are given here, the network is given, and suppose you are asked to find out the main current. Main current I is supposed to find out. So find current I. So what you will do first in this type of circuits? So straight away you would find out the equivalent resistance of this. So you can take this point as A, take this point as B, and find the equivalent resistance of this. So resistance between AB you can find out first. This is 4 ohm, this is 4 ohm in parallel. So 1 by 4, it will be 2 by 4, reciprocal that will be 4 by 2, and you will get resistance across AB as 2 ohm. This resistance is 2 ohm, this resistance is 1 ohm. Total resistance in the circuit will be equal to 2 plus 1 altogether 6 ohm. So current in the circuit will be equal to total EMF upon total resistance. So total EMF is, this is 6 volt, this is 3 volt, but they are opposing each other. So 6 minus 3 volts divided by 6. So it will be 3 by 6, which will be 1 by 2 M. So that's the main current which is to be found out. Now, if you are asked to find out potential difference between A and B, so main current into the resistance of this, you will get potential difference. If you are asked to find out what is the current through this, once you get, suppose you are asked to find out current in this arm, so current in that arm will be potential difference between A and B upon the resistance 4 ohm, that you will get the current. Okay? Likewise, I can find out the current through this. This type of situation you need to solve initially, and then you go for the difficult one. Now, sometimes instead of showing the current in the circuit, they give you ammeter. This is suppose an ammeter is shown. Here there is a voltmeter shown. So don't get confused if this type of things are there. Here they show the ammeter. Here they show the ammeter. In that case, looking at this circuit, it becomes a little bit complicated sometime for a student who initially starts studying about this. So don't get confused. This V means nothing but the voltage. This A means current flowing through this. So that you should know. Now in this type of situation, you will be told that voltmeter or ammeter involved in the circuits are ideal one. So you need not take their resistance into account. So voltmeter will be ideal, ammeter will be ideal. That type of situation, you don't take their resistances into account. Now, so other situations, suppose we have, in this situation, voltmeter is connected and you are asked to find out resistance of the voltmeter. Resistance of the voltmeter, you are asked to find out. In that case, what you can do is, you first find out, now this, in this case, this is 30 volt, potential drop is given as 30 volt, total is 60 volt, internal resistance of the cell is not mentioned, so remaining 30 volt will be across this resistor. Then you can find the current. This main current you can find out. So current will be equal to potential drop across this, which is 30 volt divided by this current I can find out. 30 volt divided by 300, it will be 1 by 10 amps. Now I want to find out resistance of the voltmeter. Resistance of the voltmeter is in parallel with this. So what is the total resistance between this? So total resistance between that is actually it is resistance across this point AB is nothing but 1 by RB plus 1 by 400. That is the resistance between A and B. So resistance between A and B will be nothing but 400 into RB upon 400 plus RB. That you substitute 400 into RB upon 400 plus RB is equal to I current into resistance. Resistance is 400 here. Okay. So, this potential drop is 30 volt. This potential drop across that is 30 volt. So, potential drop 30 volt is equal to I times this. So, 30 will be equal to I is 1 upon 10 and this is 400 into RB upon 400 plus RB. Solve this, you will get the value of RB, which is 1200 ohms. So this type of situation you need to solve. Go in detail of this type of situation. There are plenty of circuits available. Start easy one, go for a more difficult. This type of things can come in the board level exam. For a competitive exam, you have to prepare more this type of situations. Then sometimes in the competitive exam, the questions are asked on the power heat produced in the bulb. So let's try to see how one can solve this type of situation. Instead of solving just one situation, I'll tell you how one can solve many situations based on this. So let's see how to solve situations on bulbs, power, and other things. So on power, examples on power. So suppose we have a bulb. This is one bulb. This is another bulb. Okay? This bulb, this is suppose 60 watt. This bulb is say 100 watt. The power of this is P1, power of this is P2. Rating voltage is V1, rating voltage is V2. Resistance I can find out by using this. Resistance will be equal to V1 square upon P1. Because power is equal to V square upon R, so R1 will be equal to V1 square upon P1. Likewise, I can write down the resistance of this as V2 square upon P1. Please note, when you are finding the resistance of the bulb, you have to always take the voltage of the rated voltage. This is the rated voltage which is given, rating which is given. So V1 and V2 you use. Now, if this particular bulbs are connected in series, suppose. If they are connected in series, the total power, effective power in that case will be, you can find out the effective power as 1 upon P1 plus 1 upon P2. Suppose you are asked to find out the effective power. If they are connected in series across some voltage V, how to find out the effective power? You can use that particular formula. Then, suppose you are asked to find out heat generated in this bulb. If you are asked to find out heat generated in the bulb, how to find out heat generated? So first, this is sending the common current because they are in series, two bulbs are in series. The current is common. So find out what will be the heat produced in the first one. In a time, say 1 second, time will be given. So heat produced will be equal to what? You find the current, I is equal to V upon R1 plus R2, since they are in series. This is of R1, this is of R2. They are in series, so you will get R1 plus R2 as a current. Then you find out heat produced across bulb B1 heat produced will be equal to what? I square R1. Heat produced across this will be, bulb 2 will be I square R2. You can find out the heat produced. So this type of situation sometimes are asked. Of course, time will be given to you. Now, suppose you are asked if one of the bulb, if the voltage applied is very high, and if you are asked to find out which bulb will get fuse, which bulb will get fuse, which bulb will get fuse. If applied voltage is, say, if the voltage is applied is different from this, okay? So, if applied voltage, this is the applied voltage. So, you find out the current, okay, and find the potential difference across this. So, potential difference across this, bulb 1. So, I into whatever resistance bulb have. Potential drop across bulb 2, current into resistance of bulb 2. And if we find VB1 greater than V applied, check which is greater. This is suppose say 220 volt, and this is applied voltage is say 400 volt. In that case, that bulb will not support and it will get fuse. And if the potential difference you get is say 320 volt, say 350 volt, and the applied voltage is high, with the help of the applied voltage you get potential drop as 350 volt, and the marked voltage V1 is say 200 volt, 220 volt, then this particular bulb will get fuse. So we have to see which is greater, and accordingly you have to infer. I hope you have understood this. Again, I am repeating, if the voltage across the bulb is say 350 volt, you get after doing this calculation, and the rated voltage is say 220 volt. In that case, that bulb cannot support that 352 volt when current is passed with the help of this applied voltage, and it will get fuse. There are some problems which are based on if they are connected in parallel. So if the bulbs are connected in parallel, in that case, you have to calculate the power P as just add the power. And if you want to find out which will draw more current, this is suppose one type of bulb with P1, this is another type of bulb P2 having power P2, which draws more current. If V is constant, in this case parallel connection, V is constant, so power is directly proportional to I. So whichever has a greater power will draw more current. So this type of situations you can solve based on power and other thing. Now, one can use Ohm's law in simple circuit and find out the current. In previous example we have seen, if there are number of cells series or in one line opposing each other, you can find the current in the adjacent circuits very easily using Ohm's law. But there are some complicated circuit where you won't able to use Ohm's law. And solution to that, because in the electrical network there will be many loops, so many cells will be involved, and naturally you won't able to use Ohm's law as such to find the current in the different elements. In that case, we have to use what is called as Kirchhoff law. You can say Kirchhoff's or Kirchhoff laws. Now, this Kirchhoff law is the solution to solve those difficult type of situations. Gustav Kirchhoff is a German physicist who discovered this law. If you love to read Gustav Kirchhoff biography or what exactly is the contribution in physics side, it's very important to know, beside these laws, he has many other things credit to his discovery to his credit. For example, along with another chemist, he discovered rubidium also, cesium and rubidium. Not only that, he is a pioneer of spectral analysis. The spectral analysis, he was a pioneer, and he also more or less studied what is called as chemical composition of the sun. what exactly is there in the sun atmosphere. So his spectral analysis helped a lot to analyze the chemical composition of sun. So such a genius fellow he is. There are so many physicists you will, if you go through, they have done so much of contribution, and you will love to read this type of contribution from the physicists. Read this type of things so that you will get motivated to do something. Physicists like Tesla, if you try to read, my goodness, it is really loud. You will love to read his particular contribution. All know what exactly the contribution of Newton or Einstein. Try to read this also. This type of physicist stories also. Now, Kirchhoff law is the solution for a complicated loop. So in a circuit, there will be many junctions. Suppose in this circuit, there are many junctions. Okay? And these junctions, some currents will be entering the junction, some current will be leaving the junction. So in that case, how to solve the circuit? The first law is called a junction law. What does this law say? That algebraic sum of the current at the junction is 0. So suppose this is current entering the junction, this current is leaving the junction, I1 is entering the junction, I2 is leaving the junction, I3 is entering the junction, I4 is leaving the junction. In that case, algebraic sum of this current is 0. We can only find the algebraic sum of the current. So current entering the junction is taken to be positive, current leaving the junction is taken to be negative, algebraic sum of the current is 0. This is what is meant by junction law. And what exactly why it is so, the reason is, it is 0 at the junction. If it is not 0, then it will violate law of conservation of charge. So incoming currents are more and outgoing currents are less, then charge must have loss at the junction. Incoming currents are less, outgoing currents are more, charge is created at the junction. That is not possible. So that shows the law of conservation of charge is valid. What is meant by next law? Next law is the loop theorem. What is this loop theorem? Algebraic sum of the change in potential along a closed loop is 0. What does this mean? These are the various elements. If you try to find out potential drop across each element, and if you add up, it will amount to 0. But there are sign convention involved in this. So let me tell you about the sign convention. Suppose you are finding the voltage drop. This is the direction of the current. This is point A. This is point B. This is the direction of the current. Okay? And if you are traversing a circuit, if you are traveling in a direction of the current, you take potential drop as negative. Potential drop across any element is the current in that element into a resistance. So current in that element is I, resistance is R. In that case, you take potential drop as negative. If you traverse a circuit against the direction of the current, this is in a direction of the current. If you traverse a circuit against the direction of the current, then you take potential drop as positive. Okay? Potential drop as positive. So here you take a potential drop negative, and here you take potential drop positive. Now same thing if you try to apply for a battery. For a battery, you should take, if this is a battery, this is A, this is point B. If you try to go against this way, the EMF of the battery, if you go again this way, then EMF of the battery is taken to be negative, and if you go in this direction, this way, then EMF you take it positive. So if you go from negative to positive, you take EMF positive. If you are going from positive to negative, you can take the EMF as negative. And if you have a capacitor, this is plus Q, this is minus Q, this is minus Q, this is plus Q. If you have a capacitor, in that case, capacitor, you know, voltage across the capacitor is Q by C, voltage across the capacitor is Q by C, Apply the same rule. If you are going this way, you take negative. If you are going opposite from negative to positive, if you are going this way, negative to positive, you take it as positive. Okay? So if you use these simple rules, this is a main rule and these are the sign convention which we have to adopt. And if you use this in this example to solve, it will be very easy to understand and find out the current in the circuits. So first, let's try to apply this in the circuits. So I take, this is suppose A, B, C, D. I am taking this closed loop. So we are taking a closed loop. A, B, C, D, A. We are taking a closed loop A, B, C, D, A. I start from this point. First element I get from A to this, first element I get is E2, cell, potential drop across the cell is E2. Now, tell me, E2 should be positive or negative. So I'm going from negative to positive. So when I go from negative to positive, I should take EMF positive. Then, what is the potential drop across the resistance R4? It will be I4 R4. Now, I am going in a direction of the current. So when I go in the direction of the current, the potential drop is negative. So it is negative. Likewise, here I am going against the direction of the current. Potential drop across R3 is I3 R3 and it is positive because when I go against the direction of the current, potential drop is positive. And then again here we are going from positive to negative. When we go from positive to negative, you have to take EMF negative. So E1, again here the current is suppose I2. So it will be here. I am going against the direction of the current. So plus I2 R2 all amount to 0. So this is the way one can apply loop theorem. And then if the values are given to you, you can easily find the answer to the currents, values of the current. Now let's take up this particular circuit. I'm not going to solve total circuit as such, but I will help you how to take the loops and you can easily continue. So this is suppose A, B, C, D. So first loop I'll take as A, B, C, A, B, D, A. So I take a closed loop, A, B, D, A. So if I start from here, A, I get a cell. I'm going from positive to negative. You take -1. I have 1 ohm resistance here. I1 is the current. I1 is the current. I can take, it is I1, 1 into I1 in a direction of the current, negative. Then I have this 2 ohm. This current is coming. This current is leaving. What is the current in this? It will be I1 minus I2. I1 is entering, I2 is leaving. So it will be what? 2 into I1 minus I2. And this will be negative because I am going in a direction of the current. I reach here, from here to here. From here to here up to this, it will be current I1, please understand. It's not that after the resistance the current will get different, no. In this whole segment the current will be I1, in this whole segment current will be I2 unless there is any other branching taking place. So that you should understand. So this particular I2 is coming this way. So if I reach at point D, here again it is 2 into I1. I am going in a direction of the current, negative. And I am going from negative to positive, so I should take 2 volt, that is 0. And that amount to 0. Then I can take a closed loop, B, C, D, A. This closed loop I can take and start from here, from negative to positive. This is suppose 2 volt. So this is negative to positive, so you take 2 plus 2. This is suppose 1 ohm again. So 1 into I2 minus 1 into I2. This is minus 1 into I2, same current flows. And this is, we are going from positive to negative, it will be minus 1 volt. This is equation 1, this is equation 2. Solve this both the equations, you will get the value of I1 and I2. Only thing you should know to solve simultaneously. And then you can go for this type of circuit also. Choose this loop, see what are the currents here. Suppose you are asked to find out potential drop across the capacitor is how much. Take this loop, apply, see what is the incoming current here, accordingly see the current which is flowing, and you can find out the potential drop across the capacitor. So this type of many situations you can solve. Now, some more examples also are there here. One can go through this network. These are the different examples. If you just try to find out, use the law and get it. This particular example I have specially taken out on the slide for simple reason. This is a situation from semiconductor devices. So in semiconductor devices, there is a transistor involved. If you want to find out the voltages or current involved here, you can use a loop theorem to this external circuit here. So this type of thing you will be doing in the other chapters. So that's the reason I say current electricity is the focal point of the syllabus of 12th standard, because the concepts will be every now and then, formulas will be used every now and then where there is a current or current flow is involved. So these situations you can go through. There are plenty of situations. You just need to go through those situations. Now we'll move towards electrical measurements. There are different electrical measurements we need to do. And this electrical measurements one can have. The first electrical measurements circuit which we can use is a Wheatstone bridge. Wheatstone bridge is a circuit with the help of which you can find out the resistances. Unknown resistances you can find out. So what exactly is the Wheatstone bridge? Wheatstone bridge is the circuit consisting of 4 resistances P, Q, R, S. P, Q, R, S, they are arranged on 4 sides of the quadrilateral, and you can find the unknown resistance in terms of these 3 known resistances. So if there are this resistance, and this resistance is known, you can easily find out the unknown resistance. Now, what exactly? So this is a bridge. This is bridge ABCD. 4 resistances are there. The current is supplied with the help of this battery and the plug key, and between B and D there is a galvanometer connected. Now, how to find out, how to get what is called as balancing condition. Now, if you try to see the initial circuit like this, suppose we have a conductor. This is suppose a conductor, A and B, and this is connected. Across them there is a potential difference. Naturally, this is positive, this is negative, this is higher potential, this is lower potential. This is suppose C. So potential at point A is VA, potential at point C is VC, potential at point B is VB, which will be greater than VC. Likewise, on this path, on this particular conductor, if I choose a point D, potential at point A greater than potential at point D greater than potential at point C. We can find point B and D on these 2 conductors such that if you join this conductor, no current will flow from point to D, B to D. And this is what exactly is the basis of Wheatstone bridge. So if you replace this conductor by a resistance, say P, this replaced by a resistance, say Q, this is by R, this is by S, then this whole bridge is said to be balanced when potential at B is equal to potential at D. And this is what exactly the Wheatstone bridge is. So if you apply a loop theorem for A, B, D, A, you will have this relation, -1 I1P, IGG plus I2R is equal to 0. Now since B and D are at same potential, IG is equal to 0. Put that, you will get this equation. Likewise, I can apply a loop theorem to B, C, D, B, and you get this equation. Compare this equation, you will get P by Q is equal to R by S. This is called as null condition. And you can find the unknown resistance S or known resistance, any of this unknown resistance S or unknown resistance R by using this formula. This arms are called as conjugate arm, and this is what is called as null point method. So internal resistance here doesn't matter. So no involvement of the measurement of current and potential difference across the resistance of emitter, and emitter is taken into account. It's more sensitive when the resistances are P, Q, R, S are of same order, and if there are very low resistances or very high resistances, it's not so suitable to use this Wishstone bridge. So you can find unknown resistance in terms of 3 known resistances. And one more important thing, please pay attention to this part. Now, if you change the position of galvanometer and the cell and pass the current, this bridge remains to be balanced. This is the balanced bridge. P by Q is equal to R by S. We say that bridge is balanced. No current flows to the galvanometer. So P by Q is equal to R by S is called as null condition. No current will flow to the galvanometer. For this particular combination, if you interchange this, there won't be effect on the condition as such, and that's what you should need to understand. Now, modified form of this is one can solve some more examples based on this. Okay, this type of situations have figured in the previous papers. So you can just solve the example where you are putting it in series, what will be the X value? If you put it in parallel, what will be the X value? You can easily use null condition and do it. Suppose you have a resistor here, carbon resistor. Find the value of the carbon resistor, balance it, find the value of R. This type of situations are there in the previous papers. You can go through this type of situations once you do this particular part. Then, the modified form of Wishstone bridge is the meter bridge. And we have a meter bridge here. This is a meter bridge. This is a meter bridge. Now, meter bridge is having a wire. This wire AB, this is a wire AB. There are metal plates fixed here. There are metal plates fixed here. Gaps are left between the metal plates. This is a left gap. This is a right gap. This is a uniform wire. This is a uniform wire AB. Below that, there is a scale fixed. Between this gap, you can put the resistances. You can pass a current through this wire with the help of the external circuit. This is a meter bridge. You are going to experiment based on this. 2-3 experiments are there based on this. You will be using this in the laboratory. So let's try to see how one can find out unknown resistance using this meter bridge. So this is the left gap I was talking about. This is the right gap. These are the copper plates. You pass a current with the help of the external circuit. This is the meter scale which is just fixed below the wire. Now, it is working on the principle of Wishstone bridge. What is that? If point B and D are at same potential, no current will flow from point B to D, and the bridge will be said to be balanced. So, no current will flow from point B to D when the bridge is balanced. So, use this fact. So, we have R, which is here as a one resistance. It is unknown or known. S is another resistance. You can take R, S, or you can take any other notation also. So, you can take X and R, any other notation also. Suppose in the formula I have taken this as X, this as R. So, if I take that, using balancing condition, we have this as suppose X, this as suppose R. Resistance of this segment is R1, resistance of this segment is R2. Using null condition, X by R is equal to R1 upon R2. Now, sigma is the resistance per unit length of this 1 meter wire. So, you can find the resistance R1 as L1 into sigma, R2 as L2 into sigma, R1 by R2 will be L1 upon L2. And using both this condition, you will get X by R L1 upon L2. And if L2 is, this length is in centimeters, you can have 100 minus L1. The length of the wire is 1 meter. That's the reason it is not called as meter bridge, please note. It's a meter bridge. You can measure the resistances on this. So this is a meter bridge. What are the errors in this meter bridge which you have to account? You will get familiar with this particular bridge because you are going to do number of experiments. And this is not so difficult to understand. You just go to the matter, write down the equation and get this. Only thing you have to use a null condition correctly. Then there are 2 errors. these wires are fixed at the end. As I showed you in the bridge, there are wire is fixed at the end. Because of that, there is a resistance which is called as end resistance. And this wire which is there may not be uniform. In that case, that error is also arising because we are treating in this formula sigma as uniform, resistance per unit length is uniform, wire is of uniform cross section. If it is not uniform, that there might be an error. That error you eliminate by interchanging the resistance. So how you perform this experiment? Suppose you put a resistance X in this gap, R in this gap, take this jockey, this is called a jockey, which could be moved on the wire. It's a metallic contact which could be moved on the wire. Find out the point here at which the galvanometer will read 0. That distance is L1. Remaining distance will be 100 minus L1. Substitute and get the value of resistance, unknown resistance. Then, it's not very suitable to measure very low resistances. Also, interchanging the battery and the galvanometer. In the previous case also I told you, if you change the position of battery and the galvanometer at a null point, you find out the null point, you get a null point say at 50 centimeter. And then you place a galvanometer here and battery here. It won't affect the null point. You will get the null point at 50 because the current distribution doesn't change. Then there are thick copper wires here. These thick copper wires are put so that the resistance is negligible. And if you use this formula, X into L2 is equal to R into L1, one can easily find out in each direction the null point will shift. If R is increased or R is decreased, you can easily find out that. So based on this, conceptual questions are sometimes asked. So you go through this formula in detail. The next device which we have is potentiometer. Potentiometer is a device which is used to measure, you can measure EMF of the cell, you can find the EMF of the cell, you can find the internal resistance of the cell, you can compare the EMF of the two cells. So you can do it by using a potentiometer. Now potentiometer is a long wire. Potentiometer is a long wire. This is a potentiometer. There are 4 wires, 4 segments of wire. This is one end of the potentiometer. This is another end of the potentiometer. The wire is fixed on this bridge. Wire is fixed on this wooden plate. And this wire starts from here, ends up here. You can pass a current through this wire externally. Let's see what is the use of this potentiometer, how one can use it for different purposes. First case, so this is the potentiometer I am talking about. Let's see what is the principle of potentiometer. So it is, here it is 4 meters length, need not be 4 meters length. You can take any length of the wire and you can make a potentiometer. You pass a current with the help of a battery, plug key and the rheostat. And when you pass a current through this, the whole wire is having a resistance, say R dash. Sigma is the resistance per unit length of this wire. Then resistance of this wire AB is R dash upon L. Sigma is resistance per unit length, so resistance will be R dash will be sigma L. Now, if V is the potential difference between the ends of between these two ends, A and B, then by using Ohm's law, current I flowing through this wire into resistance of this wire will be equal to V. Now, R dash is sigma L, so I sigma L you will get, and if I and sigma are kept constant, then potential difference is directly proportional to length, just like Ohm's law. Just like Ohm's law, you need to know this. Ohm's law states potential difference is directly proportional to current. Here potential difference is directly proportional to the length provided current and the sigma remains constant. Their physical condition remains constant. That is, V by L is called as potential gradient. What is meant by potential gradient? V by L, and it's unit volt per meter. If you have 2 different potentiometers, if you plot a graph for this, the slope you will get potential gradient. These are the 2 different potentiometers. You can compare their slope, which has a greater potential gradient you can compare. Question based on this, you can easily understand if you know this graph plotted V versus L. Then another use of potentiometer, you can find the EMF of the cell. So if you want to find out the EMF, put the cell here, find out this length. This is nothing but balancing length. This is a galvanometer used. You move this jockey till you get a null point, no current flow through the galvanometer, and you can find out, you can, using the formula E1 is equal to potential gradient into L1, you can easily calculate EMF of the cell. So this is the use of potentiometer. Then the next use of potentiometer is to compare EMF of the two cells. Again, potentiometer is of, you can explain the construction. How it works? Very easy. You put a cell, two cells this way. There is a small resistance box here, galvanometer here, and then pass the current. First, you put cell E1 in the circuit, find out the balancing length L1. Balancing length L1 is nothing but galvanometer will read 0 when you touch at this particular point. Then find balancing length L2, and you can easily use a formula to give you E1 upon E2 is equal to L1 upon L2. Only condition is that the EMF of this cell should be greater than the EMF of these cells. Okay? So EMF of the driving cell, this is a driving battery, should be more than the EMF of those two cells. Next is how to find the internal resistance of the cell. Internal resistance we always denote by small r. So again same circuit, here I have taken many turns. Potentiometer need not be of 4 segments, it can be of 8 segments, whatever is available you take, and then you can find out what is the internal resistance of the cell. So this is a EMF, this is a cell of EMF E of which you have to find out the internal resistance. Connect this circuit. There is a, first you try to connect the circuit, put it K2 open and pass the current in K1. K2 open, pass the current K1, move this jockey till you get a null point and at N1. And you find a balancing length from this end to that null point. That you will get, say, L1, and you can write E1 is equal to K times L1. Now you put, say this key also, K2, and again find out the balancing length L2, you will get potential difference is equal to K times L2, because now cell is supplying the current to this circuit. Then E by V is equal to L1 by L2, and by using a plain formula, you can resort to a simple calculation using the Ohm's law circuit in this particular circuit, and resort to the final formula, internal resistance R is equal to capital R, L1 upon L2 minus 1. This type, simple problems you can tackle based on this. Conceptual questions could be asked based on this. Last, more or less, potentiometer is preferred over voltmeter because it does not draw any current at a null point. That's the reason it is preferred. It can measure very, very less potential difference, and sensitivity of potentiometer depends on the potential gradient. More the potential gradient could be increased or decreased by using a length of the conductor or changing the current. And when we are doing the experiment, one should not rub the jockey on the wire. Using the equipotentiality, using the conditions of equipotentiality, we can solve this type of network also. And this type of network you can solve using a simple rule. This type of complicated network, you can use a simple rule and solve this type of complicated network. Suppose I will give you simple, what are the rules which you can use to solve this network. This is suppose R, this is suppose R, this is suppose R, and you are asked to find out equivalent resistance between A and B. You take a mirror symmetry here. So current in this arm will be same, current in this arm and this arm will be same. These resistance will be useless. You can easily find equivalent resistance between this. So here, this particular loop we can solve by this way. Line of symmetry is shown, and this particular loop we can solve. This particular loop we can solve by taking this mirror symmetry. This particular loop we can solve. So this type of loops are there. Many loops are there. We can try to go through it and try to understand how we can solve this. This is when you are trying out for competitive exam. More or less that covers that covers what is called as the chapter 3, part 2. We have gone through more or less through this particular chapter. One can solve more problems with this. Yes, my dear student, I hope you must have enjoyed this particular part as well. Current electricity part 1, current electricity part 2. You must have enjoyed. Go through it, you will be able to understand certain concepts which I might have not covered up in detail. So do those things as well. Yes, so in this pandemic situation, all the stakeholders of education, they came together, whether teachers, parents, government, all the stakeholders are trying their level best to reach out to you. Media also is playing a major role, reaching out to you. So naturally, it's your turn now to work hard and give the good result. This reminds me of a situation of a young girl. Young girl has to attend a wedding ceremony every now and then. All the ceremonies she has to attend. And every time the elderly people has to tell her, it's your turn now to give us the good news. One day, in one such ceremony, she was pinched by the elderly lady saying, it's your turn now. She pinched her very hard. She cried in pain and said, I'm not going to attend any wedding parties henceforth. After some days, she was there enjoying the party. Friends asked her, Ari, you said you are not going to attend any parties. How come you are there today? She said, whenever this elderly people has to trouble me by saying, it's your turn now when I have to attend wedding ceremony, I also started doing the same thing to them whenever they have to attend funeral. It's your turn now, it's your turn now. Yes, my dear student, it's your turn now to inculcate thirst for learning and see that whatever we do, that is put to use. Thank you once again. And in these 3 chapters, you must have surely understood that physics is full of beautiful diagram, handsome derivation, gorgeous concept, awesome explanation, and mind-blowing problems. Thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.